Hello, welcome back. In the last class, we started discussing about coordinate descent methods and we considered a couple of examples. So, one of the examples that we considered was to minimize f1x, where f1x is defined as 4x1 square plus x2 square, and the other example was to minimize f2x, where f2x was f1x minus 2x1 x2. So, the difference between the two functions f1 and f2 is that in f1 the terms are separable in terms of x1 and x2, and in f2 the terms are not separable because there is a term which involves x1 and x2. So, the objective function here in this problem is not separable in terms of x1 and x2, and that is reflected in the Hessian matrix of that objective function. So, if you look at the Hessian matrix of this objective function, it is a diagonal matrix, while here if you look at the Hessian matrix, it is a positive definite, but not a diagonal matrix. So, both the Hessian matrices are positive definite, but in one case it is a diagonal, while in other case it is not a diagonal matrix. And when we used coordinate descent method to solve this problem, we saw that when we minimize f1x, we attain the solution x star in at the most 2 steps, while here we required more than 2 steps to attain the solution. So, the main problem in this case is that the Hessian matrix is not a diagonal matrix. So, is there any way to transform the problem into some other space or in terms of other variables, so that this function becomes separable in terms of the variables? And if that happens, then the Hessian matrix will be a diagonal matrix, and we would be able to use coordinate descent in that new space and get the solution in at the most n steps for a n dimensional problem. So, let us consider a general quadratic programming problem, unconstrained problem, where we want to minimize f of x, which is defined as half x transpose h x plus c transpose x, where H is a symmetric and positive definite matrix. Now, let us assume that we have a set of n directions d0 to dn minus 1, which form a linearly independent set. So, in some sense they form a basis for n dimensional space. So, they can be thought of as a basis for a n dimensional space. Now, let us consider any point x0 which is in n dimensional space. X0 can be any point. Now, we know that any point in the n dimensional space can be written as a as a linear combination of d0 to dn minus 1 and plus x naught. So, this is a representation of x in n dimensional space with respect to the basis d0 to dn minus 1 and some initial point x0. Now, suppose if we replace this x in this equation into this equation. So, use this right hand side into this equation. So, the objective function then becomes a function of those alphas, alpha 0 to alpha n minus 1. So, given the basis say d0 to dn minus 1 of n dimensional space and some point x0, we can rewrite the given problem in terms of the variables alpha, and that is given here. So, you will see that x here is replaced by the right hand side of this expression, and now we have a problem to minimize psi alpha with respect to alpha. Note that this alpha is a vector and that contains alpha 0, alpha 1, up to alpha n minus 1, and these alphas are real numbers. Each of the alphas are real numbers. So, we have a representation of x as obtained here using n real valued alphas. Okay. Now, once we have this problem, we can minimize psi alpha with respect to alpha. Now, let us use some notations. Let us denote by D a matrix which is obtained by putting D0 to Dn minus 1 in n columns of that matrix, and let us denote alpha to be alpha 0 to alpha n minus 1. Now, if you rewrite psi alpha in terms of this compact notation, what you will see is that psi alpha is nothing but half of alpha transpose D transpose H D into alpha plus H x naught plus C transpose D alpha plus half x naught transpose H x naught plus D transpose x naught. Now, x naught is a given point. Since this is a quadratic function, the Hessian matrix is constant and C is also a constant vector. So, this entire term is a constant term. So, when we want to minimize psi alpha, we can ignore this term, because this term does not involve any expression involving alphas. So, we have to concentrate only on these two terms when we want to minimize psi alpha with respect to alpha. Now, the Hessian matrix of this quadratic function is D transpose H D, and let us call that matrix as Q. So, how will the matrix Q looks like? So, the matrix Q looks like this, where on the diagonal you have D0 transpose H D0, D1 transpose H D1 and Dn minus 1 transpose H Dn minus 1, and off diagonal elements are Di transpose H Dj is the ith element of the matrix Q. Now, if you recall our earlier example where we want to minimize a quadratic problem. So, in our first case f1x was 4x1 square plus x2 square, and in the second case f2x was 4x1 square plus x2 square minus 2 x1 x2. So, if you recall the Hessian matrix was 8 2 0 0, and in this case the Hessian matrix was 8 2 minus 2 minus 2. So, in this case, because the Hessian was diagonal, we could do the coordinate descent, we could apply the coordinate descent method here and get the solution in at the most 2 steps. Well, that was not possible here. So, suppose we decide to make this Hessian matrix diagonal. So, the way to do that is that make all these off diagonal entries in this matrix 0, or in other words, whenever I is not equal to j, make Di transpose H dj to be 0. So, this matrix Q will be diagonal if Di transpose H dj is equal to 0 for all I not equal to j. Now, if we do that, then we get Q to be a diagonal matrix. So, let us assume that Di transpose H dj is equal to 0 for all I not equal to j, and then we have Q to be a diagonal matrix where you will see that all off diagonal elements are 0 and the ith entry of the diagonal is Di transpose H di. So, inverting this matrix becomes very easy, because we just have to take the reciprocal of each of the diagonal elements and put them on the diagonal. The rest of the elements are 0. So, they will remain 0 in the inverse matrix. So, ith entry of the matrix Q inverse is 1 over d I transpose H d I if j equal to I and equal to 0 otherwise. Remember that whenever we want to solve or minimize a convex quadratic function half x transpose h x plus c transpose x, what we need to is that set assuming that H is symmetric and positive definite matrix, what we do is that take the derivative or the gradient of the function and set it to 0. So, what we get is h x plus c equal to 0 and in other words x equal to minus h inverse c. So, that requires inversion of a Hessian matrix and that inversion is easy if we have H to be a diagonal matrix. So, Q inverse is like this and now if we look at our psi alpha. So, psi alpha if you recall that we had defined it to be half of x transpose h x plus c transpose x, where x is represented as x 0 plus sigma alpha I d I, where d i's are the I going from 0 to n minus 1 and d i's are the basis of that n dimensional space and x 0 is any initial point. So, this was our initial objective function and now with this condition that d I transpose h d j equal to 0. So, what happens is that the terms involving d I transpose h d j, they become 0 in this product and what we get finally is the terms involving only d I transpose h d I going from 0 to n minus 1. So, there is a coupling which was there between the d i's and d j's in this objective function, that vanishes if we assume that d I transpose h d j equal to 0 for all I not equal to j. And therefore, so what we get is that apart from the constant which we saw that we can ignore because it involves all terms involving x naught, h and c. So, we can ignore that part and what remains is the term which is shown here and now you will see that every term here in this objective function involves only one of the alpha i's, or in other words now this becomes a separable problem in terms of alphas. So, this is a very important observation that psi alpha now becomes separable in terms of alpha 0 to alpha n minus 1, because this summation which was there in the earlier term which had this coupling between d I and d j in terms of d I transpose h d j and that coupling vanishes because of this condition and we get. So, we have n terms here and each term is dependent on only one of the alphas. So, the function psi alpha is now separable in terms of alpha 0 to alpha n minus 1 and once we have this separability, it is easy to optimize this objective function individually in terms of alphas. So, let us see how to do that. So, we have this separable function in terms of alphas. So, when we want to optimize with respect to alpha, what we can do is that we can take individual alphas at a time and optimize with respect to each of those alphas. So, those alphas, so in the alpha space you can think of it as a coordinate descent method. So, we take one alpha at a time and optimize with respect to that and what we get is by setting the derivative of this to 0, we get alpha I star to be minus d I transpose h x naught plus c divided by d I transpose h d I. Okay. So, if we do it for all alphas, so we will get alpha 0 star to alpha n minus 1 star and then we can get x star by plugging in those alpha stars here in this formula to get our x star. So, computation of x star becomes very easy in this way, provided we ensure that di transpose H dj is equal to 0. So, what are these directions di transpose H dj is equal to 0? So, suppose we have a symmetric matrix which is n dimensional, then the vectors d0 to dn minus 1 are said to be H conjugate if they are linearly independent and di transpose H dj is equal to 0 for all I not equal to j. So, in other words, if we are able to get H conjugate vectors for a given quadratic function, then we can convert it to a separable problem and get these alphas very easily and plug those alphas in this formula to get x star. So, what are these H conjugate vectors? These are the vectors which are linearly independent and they satisfy this property that di transpose H dj is equal to 0 for all I not equal to j. So, if H is identity matrix, what we get is the orthogonal vectors. So, when H is identity and d0 to dn minus 1 are linearly independent, then what we have is that di transpose dj is equal to 0 for all I not equal to j. That means that the set d0 to dn minus 1 forms an orthogonal set of vectors. So, that is a special case of H conjugate vectors when H is identity matrix. Sometimes this is also called H orthonormal set of vectors. So, the vectors are orthonormal with respect to the matrix H, which is a symmetric matrix. Okay. So, these are called conjugate vectors or H conjugate vectors with respect to the matrix H. And now, let us consider the same problem formulation that we saw last time. So, we have this problem where we want to minimize 4 x 1 square plus x 2 square minus 2 x 1 x 2. So, if you look at the contours, so this is our function f of x to be x 1 square, sorry 4 x 1 square plus x 2 square minus 2 x 1 x 2. Now, we know that this is going to be x star. This is the minimum, and suppose we start from the point x 0, which is minus 1 minus 1. So, this is our initial point and we want to use we want to find out some directions d0, d1 such that we can reach from x 0 to x star. Okay, so, let us see how to do that. Now, we have already seen that the Hessian matrix in this case is this, which is not a diagonal matrix. So, let us consider some initial point which is minus 1 minus 1, both the coordinates are same, and let us consider the first direction to be the direction 1 0. So, that means we want to optimize only with respect to x 1. Now, we have already seen this that x 1 is nothing but x 0 plus alpha 0 d 0, where alpha 0 is the minimization of phi 0 alpha with respect to alpha. Remember that this alpha belongs to R, because we just have a direction d, we do not want to make this alpha to be strictly greater than 0 as we did in earlier cases. Earlier we were working with descent directions. So, we wanted to move along the descent directions and wanted to have alpha to be greater than 0. While here the direction that we are choosing, we do not know whether that is a descent direction or negative of this is a descent direction. So, we have to make alpha a real valued variable in this case, and alpha 0 is obtained by minimizing phi 0 alpha with respect to alpha, where phi 0 alpha is defined as f of x 0 plus alpha d 0. So, we used this last time and found that phi prime alpha equal to 0 implies alpha 0 is equal to 3 by 4, and we move to the point minus 1 by 4 minus 1. So, we move to the point. So, took this step and move to the point. So, this point is x 1 to be minus 1 by 4 minus 1. So, if you recall, in the earlier case we used the second coordinate direction. So, this is our x 1 and this is x 2. So, in the earlier case we used the second coordinate direction and we could not reach the solution in that case. So, let us see what happens if we use a direction which is h conjugate to the previous direction. Remember that we have used this direction as our d 0, and then we got the point in this direction, which is a minimum. Now, let us so after having found x 1 which is minus 1 by 4 minus 1, our next step is to find out the direction d 1. Now, unlike the previous case where we use the direction d 1 to be the direction along the x 2 axis, we will use the direction d 1 which will be h conjugate to d 0, or in other words we are looking at direction d 1 which is h orthogonal to d 1, or it should satisfy d 1 transpose h d 0 equal to 0. Now, how do we get this direction d 1? So, let us assume that the direction d 1 is a b, the two components of that direction, and what we want is that d 1 transpose h d 0 to be 0. So, therefore, what we want is that a b into the Hessian matrix into the direction d 0, which is 1 comma 0, that should be 0. So, if we now rewrite this in the equation form, what we get is that the a and b of this direction d 1 should satisfy this property at a minus 2 b equal to 0. So, as you can see that we have one equation and two variables, and therefore, there exists infinitely many solutions to this equation. Now, we can choose one of those solutions. So, for example, suppose we choose a to be 1 and b to be 4. So, if you recall, if we choose a to be 1 and b to be 4, that satisfies this equation. So, suppose we choose d 1 to be 1 comma 4. Now, if we use that direction, so that 1 comma 4 direction will be this is going to be our d 1. This is the direction 1 comma 4 from this x 0. Now, x2 is x1 plus alpha 1 d1, where alpha 1 is the minimum of phi 1 alpha. With respect to alpha, again I repeat that this alpha belongs to the set of real numbers, not the set of positive real numbers only. And we get f of alpha minus 1 by 4 and 4 alpha minus 1. We plug in that in the original equation, and what we get is 3 by 4 into 4 alpha minus 1 square. So, we take the derivative of phi 1 alpha with respect to alpha, equate it to 0, we get alpha 1 equal to 1 by 4, and when we use x2 equal to x1 plus alpha 1 d1 and plug in the value of d1, alpha 1 and x1, which is minus 1 by 4 comma minus 1, what we get is 0 0, which is nothing but our x star. So, if we do the exact line search along this direction, what we get is and we end up at x star. Now, compare this with our earlier approach, where for the same function so if we start from 1 minus 1, so initially we went to, so this was x0 to be minus 1 and we reach the point x1 was minus 1 by 4 minus 1, and then if we use the other coordinate, so these are the coordinates. So, if we use the other coordinate, we would reach some point which is here. Now, compare this. So, this was the coordinate descent method in the x1 x2 space, while if you look at this, that the first iteration was along the direction d0, but second iteration was along the direction d1, and that d1 was chosen such that it is h conjugate to d0, and if we do the exact line search along d0, we would end up at x star. So, this method required at the most 2 iterations to reach the solution. So, this is a very important point. So, in two steps we got the solution x star. So, in general we can say that a convex quadratic function can be minimized in at most n steps, provided we search along conjugate directions of the Hessian matrix. So, if we have this information of conjugate directions for the Hessian matrix, then if we do the search along those conjugate directions, then in at the most n steps we will reach the solution of a convex quadratic function. Now, there are some important questions that need to be answered, and one of the questions is that given H, does a set of H conjugate vectors exist? So, what is the guarantee that there exist H conjugate vectors? And suppose there is a guarantee that H conjugate vectors exist, then how do we get one such set of H conjugate vectors? So, these are the important questions that need to be answered, and we will now answer these questions. Now, if you consider a quadratic function which is convex. Now, if we look at the eigenvectors of this function, so suppose if we transform the original system or original coordinates into the new coordinates, and then if we use these as our coordinates, then we can use coordinate descent method in this new space of coordinate vectors. And if we use the coordinate descent method in this space, you can see that we can reach the solution in at the most n steps. So, this the eigenvectors of this matrix, the Hessian matrix H, is a one possible set of H conjugate vectors. Now, we will see how to show that. So, let us consider a matrix H, which is a symmetric matrix, and the question is that do there exist n conjugate directions with respect to H. Now, we know that H is symmetric means that H has n mutually orthogonal eigenvectors. Okay. So, let us take a couple of eigenvectors which are mutually orthogonal. So, let V1 and V2 be two orthogonal eigenvectors of H, and since H is symmetric, we can choose V1 and V2 such that V1 transpose V2 equal to 0, or V1 and V2 are orthogonal. Now, since V1 is a eigenvector and V2 also is eigenvector, so of H, so we can write HV1 equal to lambda 1 V1, where lambda 1 is an eigenvalue of H. Remember that this is a symmetric matrix, so the eigenvalues are real. So, lambda 1 is a real number. So, HV1 equal to lambda 1 V1. Now, if you multiply it throughout by V2 transpose V2 transpose, so what we get is V2 transpose HV1 is equal to lambda 1 into V2 transpose V1. But we know that V1 transpose V2, which is nothing but V2 transpose V1, is 0. So, that means that V2 transpose HV1 is equal to 0, and V1 and V2, they are linearly independent, and V2 transpose HV1 equal to 0. So, they form what are called the H conjugate vectors of H. So, V1 and V2 are H conjugate, and therefore, we can say that the n orthogonal eigenvectors of H are H conjugate. So, we can extend this result for all the n orthogonal eigenvectors of H, and these orthogonal eigenvectors of H, from this result you can see that they are H conjugate. Okay. So, given a symmetric matrix, there always exists H conjugate vectors, and one set of H conjugate vectors is orthogonal eigenvectors of H. Remember that this set of H conjugate vectors for a given symmetric matrix H need not be unique. This is the set of n orthogonal eigenvectors is just a one set. Now, let us look at some other properties of conjugate directions. So, suppose we have H to be a symmetric and positive definite matrix, and suppose d0 to dn minus 1 are non-zero directions such that di transpose h dj is equal to 0 for all I not equal to j. Then the question is that are these directions linearly independent? Okay. Now, to show that they are linearly independent, what we have to do is that if we take a linear combination of these vectors and equate it to 0, then all the coefficients in that linear combination should also be 0, or in other words, if we say sigma mu I di equal to 0 for I going from 0 to n minus 1, then we have then if they are linearly independent, then mu I has to be 0. So, let us consider this sigma mu I di to be equal to 0. Now, that implies that if you multiply throughout by dz transpose h, what we get is sigma mu I dz transpose h di equal to 0 for every j going from 0 to n minus 1. Now, we know that di transpose h dj is equal to 0 for all I not equal to j. So, all the terms in this expression vanish except the jth term. So, what remains here is that mu j into dz transpose h dj is equal to 0 because of the h orthogonality of the set d0 to dn minus 1. Now, H is a positive definite matrix, dj is non-zero. So, dz transpose h dj is greater than 0 and therefore, mu j has to be 0. Now, therefore, mu j becomes 0 for every j. So, which means that sigma mu I di equal to 0 means that mu I equal to 0 for all I, and that means that this set of vectors are linearly independent. So, if we have a positive definite matrix and d0 to dn minus 1 are non-zero directions, remember that this non-zero is important because in this case we want to show that di transpose h dj is strictly greater than 0, and that is possible because H is a positive definite matrix and di is non-zero. So, di transpose h dj is strictly greater than 0 and therefore, mu j has to be 0. So, if these are non-zero directions which are H orthogonal to each other, then d0 to dn minus 1 the n are linearly independent vectors in the space Rn. So, they form a basis for Rn. Now, so this is what we showed, that d0 to dn minus 1 are linearly independent. Now, let us look at the geometric interpretation of conjugate directions. Now, again let us consider the general problem in two-dimensional space. So, remember that we are considering a two-dimensional problem. So, the matrix H, which is a symmetric positive definite matrix, is a 2 by 2 matrix, and we want to minimize half x transpose h x plus c transpose x. Now, let us assume that x star be the solution of this problem. So, therefore, we can say that h x star plus c is equal to 0 because we have to take a gradient of this quantity and equate it to 0. So, gradient is h x plus c, and when we equate it to 0, that is satisfied at the solution. So, h x star equal to minus c. Now, let x0 be any initial point, and the gradient at that point is nothing but h x naught plus c, and let d0 be some direction d0. So, the idea is that we start from a point x0, use the direction d0 and do the exact line search to go to the point x1, and then at x1 we choose a direction d1 which is h conjugate to d0. That is the idea, and we want to see whether that direction is indeed a h conjugate direction or not. So, x1 is found by doing exact line search along d0, and we know that in such a case g1 transpose d0 is 0. The gradient at the point x1 is orthogonal to the direction d0. So, suppose these are the contours of a quadratic function. and this point is or x star. So, suppose that this is x naught and this direction is d1. So, since we are doing exact line search, so what we get is the point x1 to be this point, and this the g1, the gradient at x1 is so it should be d0. So, you will see that g1 is orthogonal to d0. Now let us look at this direction, the direction which we get from x1 to x. So, let us look at this direction. So, this is the direction x star minus x1, and this is going to be our d1. Now, we want to see whether x star minus x1 is orthogonal to d0 or d1 is orthogonal to d0. Now, remember that g1 is nothing but the gradient of this at x1, and that is nothing but hx1 plus c. So, x star minus x1 transpose h d0, that is what we are interested in finding out. What is this direction? We know this direction x star minus x1, we had earlier chosen d0. So, what is this expression x star minus x1 transpose h d0? Now, if you look at this expression, so x star is nothing but x star is nothing but minus h inverse c, or we can bring in h inside and write this as hx star minus hx1 transpose d0, and this hx star is nothing but minus c. So, what we have here in this expression in the parenthesis is minus c minus hx1, and minus c minus hx1 is nothing but minus g1. So, what we have is minus g1 transpose d0, and we know that x1 was found by doing exact line search along d0. So, therefore, g1 transpose d0 is equal to 0, and therefore, this quantity is 0, and therefore, x star minus x1 is h conjugate to d0. So, in other words, so this direction x star minus x1 is indeed h conjugate to the direction d0. So, this direction is so this d1 is chosen, which is h orthogonal to d0, and if we do now the exact line search along this direction d1, so what we get is that we move up from this point to this point and end up at the minimum, which is x star. So, at the most 2 steps were needed here to reach the solution. So, this is a geometrical interpretation of conjugate directions. Now, let us again consider the same problem, a quadratic programming problem where the Hessian matrix is symmetric and positive definite matrix, and Let us assume that d0 to dn minus 1 are H conjugate. Okay, so suppose we have already got this H conjugate directions. Now, how does this method work when we use this H conjugate directions? Remember that d0 to dn minus 1 are H conjugate and therefore linearly independent, and we have shown that. So, they span the entire n dimensional space. So, is it possible to do the minimization with respect to each of the directions one at a time? So, we start from x 0, move along the direction d 0, go to x 1, then move along d 1, go to x 2 and so on. So, is it possible to get a minimum at the end of searching through dn minus 1, and that is possible, and this is what we are going to see now. So, we have already shown that these directions which are H conjugate means that they are linearly independent. So, let us denote by script Bk the subspace of Rn spanned by d0 to dk minus. Though these are k vectors and they span a k dimensional space of real numbers, and which is a subspace of Rn. Now, clearly the Bk space is a subset of Bk plus 1, because Bk plus 1 will have an extra vector dk which is independent of this. So, the dimension of this subspace is one more than the dimension of this subspace, and this is a subset of the set Bk plus 1. Now, let us choose any point x 0 in n dimensional space, any arbitrary point, and as usual we use this formula where x k plus 1 is set to x k plus alpha k dk, where alpha k is obtained by doing exact line search, and I repeat that this alpha is over all possible set of all possible real numbers. So, one has to search over all possible set of real numbers, the alpha which minimizes f of x k plus alpha dk, and that minimum value of alpha or that value of alpha which gives the minimum of f, let us denote it by alpha k, and if you use that alpha k here and find x k plus alpha k dk, we get x k plus 1. Now, the claim is that the x k that we obtained by minimizing f x over the space which contains x 0 and spanned by d 0 to dk minus 1. So, x k is the minimum over this subspace. So, if we want to extend this result, that means that what it means is that x n will be the minimum of f x, where x belongs to x 0 plus b n, and b n is nothing but the space spanned by d 0 to d n minus 1, and that is the entire space, because d 0 to d n minus 1 are linearly independent set of vectors. So, that spans the entire R n. So, what this result means is that if you search along the directions d 0 to d n minus 1, which are H conjugate, and every time if you do the exact line search, then after doing at the most n line searches, assuming that we have not reached the solution in that n line searches, at the end of nth line search, we will have reached the solution. So, let us see the interpretation of this result. So, suppose this is the point x 0 and this is the direction d 0. Now, we do the exact line search along this direction to get the point x 1, and then we so what it essentially means that So, this d0 is a non-zero vector. So, it spans a one dimensional space. So, in this one dimensional space x1 is the minimum. Now, we take another vector which is say d1. Now, d1 and d0 are independent. So, they form a two dimensional space. Now, what the claim is that when we find x2 by doing exact line search along the direction d1, we have minimized the function f in the two dimensional space spanned by d0 and d1. So, that space, so let us denote it by this, and then we go to the vector d2. So, that d2 could be a vector which is independent of d1 and d0, but remember that d2 will now be H conjugate to both d1 and d0. So, this will be a vector d2, and now that span d0, d1 and d2 being linearly independent, they span a three dimensional space. So, again the claim is that when we move from x2 to x3 to get a new point x3, we will have minimized the function fx over the space spanned by d0, d1 and d2, and that is a three dimensional space. So, every time we add a H conjugate vector to this set d0, d1, d2 and so on, and we will have minimized the function in the respective k dimensional space. And if we repeat this procedure n times, and if at any point of time the gradient does not of the function does not vanish, that means at the end of nth iteration, when we reach xn, we will have found the solution of the given problem. So, this property is called expanding subspace property, and the important point that one has to remember is that whenever we get xk, we have solved the problem completely with respect to the k dimensional space spanned by d0 to dk minus 1, and that space which contains x0. Note also that we have chosen x0 to be any arbitrary point. So, the initial point is not going to matter when we do this, and if the process is repeated n times, then the claim is that at the end of nth iteration or n line search, we will have got x star, the minimum of this objective function. Now, let us prove this result. So, suppose that alpha k is obtained as minimum of f of x k plus alpha d k, where alpha belongs to R. Now, since it is obtained using an exact line search, so if we define phi alpha to be f of x k plus alpha d k, then phi prime alpha equal to 0 implies that gradient of f of x k plus alpha k d k transpose d k equal to 0, and this is nothing but x k plus alpha k d k is nothing but our new point x k plus 1. So, g k plus 1 transpose d k is equal to 0 for all k going from 0 to n minus 1. Now, the important point that you have to remember is that so the gradient at the new point, which is g k plus 1, is orthogonal to the gradient orthogonal to the previous direction d k, and this is true for all k going from 0 to n minus 1. Now, in addition to this, what happens is that g k plus 1 transpose d j is equal to 0 for all j going from 0 to k minus 1. So, not only that g k plus 1 is orthogonal to d k, but gk plus 1 is orthogonal to all the previous directions d0 to dk, which are the k plus 1 directions. So, the gradient at a new point is always orthogonal to the subspace spanned by d0 to dk. So, this is what we are going to show, and then we show that when we minimize f of x over the subspace, we will get xk, that is obtained by minimizing f of x over this subspace. So, if we do this, we indeed get a xk which minimizes f x over x belongs to x0 plus pk. So, we will see that proof in the next class. Thank you.